Welcome to the online contents of BCA Knowledge Kotek. Today we are going to discuss continuous uniform distributions. And the learning objectives for this session are introduce continuous uniform distributions, derive its properties, and then we will see some of the applications of this uniform distribution. Before we start, we will have a quick look of what is a continuous distribution is. It is the distribution function associated with the continuous random variables. And we had seen what is a continuous random variable. It is a variable or it's a random variable which can assume uncountable number of values. And we had seen so many examples for this one. For example, the length of a randomly selected hair of a hair, or it may be the duration of an online class, and some of the examples for these continuous random variables. And before we start, the distribution function in the case of a random variable is defined as, and it is denoted by capital F of x is equal to probability that the random variable x assumes a value less than small x, where small x can be any real number. And for any continuous random variable, you have to keep in mind that the probability associated with the particular value, a probability of x is equal to c, is equal to c irrespective of the distribution. Whatever be the distribution, if it is a continuous random variable, probability of x is equal to c equal to 0. With this in mind, we will move on to a rectangular or uniform distribution. Continuous uniform distribution is also called rectangular distribution. A continuous random variable which assumes every value with equal probability, need not be value, every range with equal probability is called uniform. That is why it is called uniform. The probabilities are constant throughout. A continuous random variable x is said to follow the uniform distribution over the interval a to b. Then the density function is given by f of x is equal to 1 by b minus a less than or equal to x less than or equal to b, and 0 otherwise. We can see that whatever be the random variable which can assume, the random variable can assume in between this range a to b, the probability density function remains to be the constant. Hence, it is called uniform random variable. And you can see that when we plot the density function against the AB real line, we can see that at the point of A and B, we will have a rectangular shape at there. So it is called a rectangular distribution. It doesn't matter whether the strict inequality holds at the boundary points, because we had seen that the probability that a continuous random variable assumes a particular value equal to 0. So probability of x is equal to a is absolutely equal to 0, as well as probability of x is equal to b equal to 0. So it doesn't matter whether we take probability, whether we take it is equal to less than or equal to, or less than or equal to. Now, as mentioned earlier, now we will see the basic properties of this distribution, including the mean. We have defined the expectation of x to be as integral a to b, or integral over the range of x into f of x dx, and that is equal to integral a to b x into, here f of x is equal to 1 by b minus a into dx, and we can see that this b minus a is constant, so it comes out, now it becomes b minus a into integral a to b f of x dx, and now integral x dx is equal to x square by 2, so it becomes 1 by b minus a into x square by 2 within the limits a to b, and it becomes 1 by b minus a into b square minus a square divided by 2, and we know that b square minus a square is equal to b minus a into b plus a, and that is equal to 1 by b minus a into b plus a into b minus a divided by 2, and we can see that these both b minus a will cancel off, and that is equal to a plus b divided by 2. On the uniform case, we can see if we define the mean as a center of gravity, momentum, as the first moment, center of gravity, then we can see that if the distribution, if you take the example of a rectangle, we can see that the rectangle will balances at the midpoint. So it shows the same thing. The expectation, as you know, that the expectation is nothing other than the center of gravity, so it balances at this particular point. Now we will go for deriving the variance of this distribution. For that, we will consider expectation of x square. As proceeding as in the earlier lines, we can see that expectation of x square is equal to, by definition, that is equal to a range of x square into f of x dx. Here f of x is equal to 1 by b minus a, and we will take this b minus a out, then it becomes integral x 1 by b minus a into integral x square dx. On integration, integral x square becomes in x raised to 3 divided by 3 within the limits a to b, and on substitution we can see that that becomes 1 by b minus a into, when we substitute the upper limit it becomes b cube, and when we substitute the lower limit it becomes a cube, so b cube minus a cube divided by 2. And we had seen in the elementary classes that the expansion of b cube minus a cube as a minus b into b square plus ab plus a square divided by 3. That 3 comes from the other part also. Now b minus a, b minus will cancel off, and that is equal to, and expectation of x square is equal to b square plus ab plus a square divided by 3. Now we will move on finding out the expectation variance of this one. Now we have defined the variance of x to be as expectation of x square minus expectation of x the whole square, and we have derived the expectation of x square to be as b square plus ab plus a square divided by 3 minus a plus b divided by 2 the whole square, because we are having expectation of x the whole square. Now this is equal to b square plus ab plus a square divided by 2 minus, we will expand this a plus b the whole square equal to uh, a square plus b square plus 2ab divided by 2. I hope you remember this expansion. സ്ഫടികത്തിലെ ചക്കമാഷ് പറയുന്നത് പോലെ ദ്വിമാന സമവാക്യത്തിന്റെ എക്സ്പാൻഷൻ ആണ്. So that is equal to, now we can see that we will go for the LCM on both sides. I mean LCM of LCM. So to solve this one, we can see that the LCM of 4 and 3 are 12. So it becomes 4 into b square plus ab plus a square minus 3 into a square plus b square plus 2ab divided by 12. So that becomes, we can see that 4b square minus 3a square is there. So only, 4b square minus 3b square is there. So only one b square will remain. And one, similarly the case with a square. And we can see that 4ab minus 6ab is there. So the on expansion it becomes b square minus 2. On simplification it becomes b square minus 2ab plus a square, or that is equal to a minus b the whole square divided by 12. So the variance of a uniform distribution or a continuous uniform distribution or rectangular distribution equal to b minus a the whole square divided by 2, or equal to a, or it is equal to, as we are taking the square, it is equal to a minus b the whole square divided by 2. Now we will go on for finding out the basic another property called moment generating function. We have defined the moment generating function mx to be as expectation of e raised to tx, and it is nothing other than integral over the range of variation of x e raised to tx into f of x dx. And here we can see that f of x is equal to 1 by b minus a, so that is equal to 1 by b minus a into dx. And we can see that this b minus a comes out as constant, and then we have integral a to b e raised to tx dx. So e raised to tx, integral of e raised to tx is e raised to tx divided by t divided by the derivative of tx, that is equal to t. So that is equal to 1 by b minus a into e raised to tx divided by t within the limits a to b. So that is equal to 1 by b minus a into e raised to bt minus e raised to at divided by t. 1 by b minus a into e raised to bt minus e raised to at divided by t. And that is equal to, on simplification we can write it to be as e raised to bt minus e raised to at divided by t into b minus a. Now we will derive the distribution function of the function, uniform distribution. We have defined the distribution function to be as probability of x less than or equal to x, which we have already seen, and now that is equal to integral a to b small f of x into dx. That is by the property of distribution function or interrelationship. Now that is equal to integral a to b f of x. We can know that it is equal to 1 by b minus a dx, and that can be taken out, so it becomes 1 by b minus a into x. When you integrate, it becomes x within the limits a to x, so that is equal to 1 by b minus a into x minus a, that, or simply that is equal to f of x is equal to x minus a divided by b minus a whenever a lies between a and b and 0 otherwise. It doesn't matter whether it is a less than or equal to x less than or equal to b, as mentioned earlier. Now we will see some of the special cases of this continuous or rectangular distribution. First one is called uniform, a standard uniform distribution. That is a case where a equal to 1 and b equal to, sorry, a equal to 0 and b equal to 1. So standard uniform distribution is the case where b equal to 1 and a equal to 0. And then the density function becomes, you know that the normal form within the uniform a to b, in the case of uniform a to b, it was 1 by b minus a. So b equal to 1, a equal to 0, it becomes 1, and the range of variation is 0 less than x less than 1. And its mean is equal to, we have derived the mean in the case of a normal uniform distribution over the range a to b as a plus b divided by 2, and here it becomes 1 by 2. And the variance to be as, earlier we derived it to be as b minus a, or a minus b the whole square divided by 12. Here it becomes 1 minus 0 the whole square divided by 12, that is equal to 1 by 12. So the distribution function, earlier it was x minus a divided by b minus a, x minus 0 divided by b minus 1 minus 0, so that is equal to x. Now the second special case is where a equal to minus a and b equal to a, uniform over the range minus a to plus a. So this is a symmetric distribution case, and here f of x is equal to 1 by a minus a, so it becomes 1 by 2a within the range minus a less than x less than a. 1 by 2a, how it comes, is equal to 1 by a minus 1 minus of minus a, so it becomes a plus a, that is equal to 1 by 2a. Mean is equal to a plus b divided by 2, a plus minus a divided by 2, it is equal to 0. Variance is equal to b minus a the whole square divided by, or a minus b the whole square, so it becomes b minus a the whole square divided by 2, that is equal to a square 4, a square divided by 12, that is equal to a square by 3. Now distribution function is given by x plus a, x minus b, so b was is equal to minus a, so it becomes x minus minus 1, so it becomes x plus 1 divided by 2a and 0 otherwise. Now the distribution function. Now we have a basic and very important theorem saying that for any continuous random variable x, irrespective of the distribution, for any continuous random variable x, the distribution function f y equal to f of x is distributed as standard standard uniform distribution. Whatever be the distribution, maybe something like it should be continuous. That is the only condition we are having, and these conditions or this theorem has very much applications in the random number generation and everything. And we are going to prove this one. Now we can see that we are applying a transformation of the random variable y equal to f of x. We are transforming the random variable x to y. So when we consider the transformation of random variables, we know that there are two methods for dealing with these situations. One is Jacobian transformation method, and the other one is using distribution function. Now the transformation, here we can see that y equal to f of x transformation is 1 to 1. Therefore, we can make use of Jacobian transformation, and so the distribution function. So here we will take y equal to fx of x, distribution function associated with the random variable x, and dy by dx is equal to, we can see that the derivative of the distribution function is nothing other than the distribution function. We are not assigning, or we are not specifying, or we are not assuming any specific form for this distribution function or density function. We are just assuming that it follows continuous distribution. It is a continuous distribution. So therefore, we can take dx by dy is equal to inverse of dy by dx, that is equal to 1 by density function. And now, as the distribution function is probability, range of y ranges from 0 to 1. We can see that y is a distribution function, And by the property of distribution function, we know that the range of y is over the range 0 to 1. Therefore, we will go for, now we will go for the density function of y. And by the Jacobian transformation, we know that fy of y is equal to fx, x in terms of y, into 1 by, sorry, into dx by absolute value of dx by dy. So that is equal to fx x in terms of y divided by fx x in terms of y. Because derivatives, we had seen that it is already equal to fx of x, and both these quantities will vanish off, and it is 1 within the range 0 to 1. And we can see that that is nothing other than the standard uniform distribution. This is the density function of a uniform random variable over the range 0 to 1, which is called the standard uniform distribution. Now we will see some of the basic problems, or some of the basic applications of this uniform distribution. If the mean and the variance of a uniform random variable are respectively 1 and 3, find the parameters of the distribution. If you find out the parameters of the distribution, we can find out the probability, any probability associated with the distribution. So we can see that mean of the random variable between a and b is a plus b divided by 2, and variance is equal to b minus a, the whole square divided by 12. So therefore expectation of x is equal to 2 implies that a plus b divided by 2 is equal to 2, implies a plus b is equal to 4, and variance of x is equal to b minus a the whole square divided by 12, so that is equal to 25 divided by 3, implies b minus a the whole square is equal to 100, and b minus a is equal to plus or minus 10. And we will simplify further. B minus a, we will say a plus b is equal to 4, and b minus a is equal to 10. When we assume, or we will solve this one, when we assume b minus a is equal to minus 10, we will get 2b is equal to minus 6, or b is equal to minus 3, and a equal to 7, which is contradictory because we are assuming that a is less than b. Hence, we will solve b minus a is equal to 10, and 2b is equal to b minus a is equal to 10, and when we add these equations together, we will get 2b is equal to 14, implying b equal to 7. Then a equal to 4, a equal to 4 minus b, that is equal to a is equal to 4 minus 7, that is equal. Hence, we derived the parameters of the given distribution as a equal to minus 3 and b equal to 7. So, today we introduced rectangular or continuous uniform distribution, and we had seen its properties like mean, variance, moment generating function, and we had seen some of its special cases, and we derived one of the most important theorems in random number generation, that is, for any continuous random variable x, f of x follows standard uniform distribution, and that's all. And we had seen some application of it. Further applications we will be seeing in the coming sessions, and in the coming sessions we will see some other continuous distributions, including normal distribution. Thank you.